Hello and welcome to WinXAS Tutorials, where I want to talk about EXAFS analysis again. This time about using theoretical phases and amplitudes for performing EXAFS simulations and refinements, not only to the first but also to higher shells in the radial distribution function. As always, the WinXAS software and the XAS data I will be using in the hands-on session can be obtained from the WinXAS website. Including higher shells in EXAFS simulation and refinement quickly increases the number of scattering paths required to describe the experimental spectrum. Not only single scattering paths where the photoelectron is scattered directly back to the absorber, but also multiple scattering paths need to be considered. In most cases, it will not be possible to extract experimental phases and amplitudes for higher shells, which tend to heavily overlap in the radial distribution function. This is the realm of theoretical phases and amplitudes calculated by an external software and used by WinXAS for EXAFS analysis. The corresponding interface in WinXAS uses phases and amplitudes calculated by the software FEFF. Documentation and further information can be found on the FEFF website. Note that any FEFF version, including older versions, capable of calculating EXAFS and generating output files containing phases and amplitudes will do nicely to be used with WinXAS for EXAFS simulation and refinement. Programs you may want to use are Atoms to generate a FEFF input file from crystallographic structure data, and FEFF itself to calculate the phases and amplitudes for the structure. When using FEFF, make sure to obtain the individual output files in ASCII format by selecting the corresponding setting in the print line. Details can be found in the FEFF documentation. Anyway, all FEFF files you need for these tutorials are included in the data folder. EXAFS refinement using theoretical phases and amplitudes from FEFF occupies the larger part of the EXAFS fit dialog box that we already saw in the previous tutorial about experimental phases and amplitudes. Because theoretical phases and amplitudes can be employed to analyze higher scattering shells, many more options are available for EXAFS refinement, and we will talk about most of them in the hands-on session. The necessity to include multiple scattering paths in addition to single scattering paths in EXAFS refinement of higher shells results in an increase of parameters. The total number of parameters can quickly exceed the number of independent parameters, which, as stated before, is more like an upper limit than a reliable quality indicator. Therefore, useful and convenient correlation schemes are required to reduce the number of free-running parameters in the refinement, while still yielding meaningful structural information about your sample. These correlations are summarized in this table with a decreasing number of free-running parameters from top to bottom. Most of these methods revolve around correlating parameters of multiple scattering paths to those of the constituent single scattering path, or setting parameters to values obtained from references or crystallographic data. The former enables us to include all necessary multiple scattering paths in the refinement without exceeding the number of independent parameters. The table of parameters from the previous slide translates to this box in the software. Given the large number of options when including higher shells in EXAFS refinement, this box needs to be more complex than the one used for single shell fits with experimental phases and amplitudes. While we will introduce most of these options in the hands-on session, Applications and benefits of many of them may become more apparent when we look at EXAFS spectra of more complex samples in future tutorials. As shown previously, EXAFS refinement using theoretical phases and amplitudes can also be performed in the K or the R space using various K weightings for fitting or display purposes. While exploring the effects of these approaches on fit results and parameters will not be the subject of this tutorial, feel free to experiment with those settings yourself. Coming next is the hands-on session. Objectives will be EXAFS analysis of copper spectra using theoretical phases and amplitudes for the first shell and subsequently also for higher shells in the radial distribution function. The copper spectra and theoretical phases and amplitudes used are included in the tutorials data folder, which can be obtained from the WinXAS website.
Let's get started with the copper foil chi of k. First step is Fourier transformation, since we will be doing all the calculation and refinement in the R space. Going to restrict the range to 6 angstrom, okay, and calculate the radial distribution function. So next step now is EXAFS simulation using theoretical phases and amplitudes. We will start with the first shell only and then later expand to include the higher shells and multiple scattering and single scattering shells. So let's start with a simulation, and now we are going to use the top part of this dialog box. So this is for theoretical phases and amplitudes calculated with the software FEFF. The files are included in the tutorial data folder under FEFF EXAFS fitting. You will find copper foil, and this contains all the phases and amplitudes for single scattering and multiple scattering shells that we need for refinement and simulation of copper metal spectrum. FEFF generates a number of ASCII files provided you choose the right flag in the print line for the output. The one file that we are using here is called files.dat, and it contains a list of all the ASCII files with or containing phases and amplitudes that FEFF has generated. So this is the file you want to be looking for, and we can open it, and we obtain this list here. This is basically what was in this ASCII file. It's a list of all the files that FEFF, that the calculation has generated for the copper metal model structure. So for the time being, we only want to select the first shell. So the first shell here with a ratio of 100, that's the strongest shell, corresponds to the first shell in this radial distribution function as indicated here by this bar. And we want to include this in the refinement. So the way that this works is on the left side you see all the files included in the files.dat that you have opened for FEFF calculation. From this list of files now you can select the number, you can select all of them or just some, and include them in the refinement. You can even open more than just one file stud, select the files, that select the scattering paths you want to include, and collect them or have them all here in this box on the right. And those included here, those are the ones that are being used then in simulation and refinement. So to get started, we only want to use the first shell. So click on transfer, and so this is the first shell, the first scattering path that we want to use. We get some information here. It's a single scattering path, copper absorber, and the copper backscatterer at a distance of 2.556 angstrom. So this is all we want to have for the time being. So we can just click on OK. We get this box to now select the starting parameters. For each shell, each scattering path, we have coordination number, distance, a Debye-Waller factor, and any zero shift. In addition, and in contrast to using experimental phases and amplitudes, we have a scaling factor, S0 square, scaling factor. And since those two are very strongly correlated, the coordination number and the scaling factor basically are just multiplier to the amplitude. They're very strongly correlated, so one of them needs to be fixed in the refinement. But for the time being, we are only doing a simulation, so we can just, okay. And now we have the red trace is the experimental radial distribution function, and the blue trace is the calculated radial distribution function together with the imaginary part of the Fourier transform. So apparently, there's a huge difference in amplitude. If we just go back to the parameters, we see we have a Debye-Waller factor of 0. So when using experimental phases and amplitudes, I said that this Debye-Waller factor is basically, it's a difference between the disorder in the reference and the disorder in the sample. Here it corresponds to the disorder basically at 0 Kelvin. So this is always a positive number as long as you are measuring at temperatures above 0 Kelvin. This will always be larger than 0, corresponding to some thermal disorder or static disorder in your sample. So we can increase this, for instance, to 0.006, and this significantly decreases the amplitude. So now what we can do is we can make use of this window that permits changing the parameters stepwise, and we want to use this for the first shell. We want to adjust the Debye-Waller factor a little bit, so we increase that some. So, and now we still see we have this difference here in the imaginary part, in the roots of the imaginary part. So this is basically, this is the frequency, so we need to change either the distance or the E0 shift. If we change the distance, we will notice that although this changes the imaginary part, it also changes the magnitude. And it shifts the magnitude to smaller distances. So that's probably not what we want. So the next thing now is the E0 shift. And here we just go with some number, let's say 5, apply. That already shifts it into the right direction. Probably here, and now we can adjust the distance, and now we need to decrease here a little bit, and then we can increase the Debye-Waller factor a little bit. So, and now this is already much better than it needs to be for starting parameters for the refinement. But you see, already by hand we can reach a pretty good agreement here between theory and experiment. Okay, so good enough, definitely, to start the EXAFS refinement now of the first shell. We go to EXAFS, refinement, and now, similar to using experimental phases and amplitude, we have to set a border. So we have to select a range in the radial distribution function where we want to perform the refinement actually. We're only including a scattering path for the first shell, so we can basically calculate or only calculate the difference between experiment and theory for the first shell. So we need to select that. There's a pre-selected range here based on the shell or the shells that you include in the refinement, and that is more often than not sufficient, and you can just take this. And okay. Now we want to do a fit, a refinement. So now we have to deal with a strong correlation here between the amplitude reduction factor and the coordination number. We cannot have them both very independent in the refinement. You may want to try that and see what results you get. Also calculate the correlation. After that, the confidence limit. But just take my word for it that they are very strongly correlated, and we want to fix either one or the other. And we're going with the amplitude reduction factor. We're going to fix this. And the other parameters, they are sufficiently independent from each other. So we just click on OK and start the refinement. So again, on the right, we have the radial distribution function, experiment and theory. And on the left, we have the same in the K space. So the EXAFS chi of K, experiment and theory. And again, this is only for display purposes. There is no refinement or calculation performed in the K space. So can click on OK. And yeah, we can calculate the confidence limits now for this refinement. This should be straightforward, and we see we have low confidence limits here, so a narrow confidence band, if you wish, and this indicates reliable structure parameters, some correlations, but nothing major, so basically independent parameters with good confidence limits. So since this is the copper metal foil, we can of course compare those parameters to the crystallographic values. We would expect a 12, a coordination number of 12 here in the refinement, and distance, the Debye-Waller factor, and we get an E0 shift. Note that this is E0 shift here in the EXAFS refinement using theoretical phases and amplitude. It's basically only a scaling factor to the calculation. It's mostly a scaling factor to the calculation. It should vary in the range between, let's say, 10 and minus 10 or 5 and minus 5, and it should not exceed that range. If it gets much larger than that, you may want to change the E0 that you use to transform your spectrum from the energy range to the K range. Yeah, this will affect this parameter because, as I said, this is basically scaling parameter that scales to the E0 threshold of the calculation. So that's already quite a good agreement between experiment and theory here, and quite similar to what we obtained with the experimental phases and amplitudes. So let's try another fit to the first shell of the copper metal foil radial distribution function. For that, first we restore the original parameters, and then we go back to refinement. Don't need to do the simulation again. We can use the same range in the R space, all the settings remain, and just click on OK. So we have our amplitude reduction factor, coordination number, the Debye-Waller factor. We have several options to calculate the Debye-Waller factor. We can just use it as a value as we did in the first refinement. An alternative is to use one of the models that are available in WinXAS that were taken from the literature, common models to be used to calculate the bi-Waller factors for EXAFS refinement. And one of them is the correlated debye model that uses this model, and it refines the debye temperature, and from that calculates the bi-Waller factor. So we use the debye model, we go up here and we select the POT button in the column of the bi-Waller factor. That changes the color and it substitutes the bi-Waller factor with the debye temperature. That is now the parameter that is being refined in the EXAFS refinement. We need to fix the amplitude reduction factor, and now we can just start the refinement. Again, we get a good agreement between theory and experiment, and no, not this time. And this is the bi-Waller factor now, and up here we do see the debye temperature that we obtained with this refinement for copper metal, and this 345 Kelvin is actually quite close to tabulated values for the debye temperature of copper metal. So again, good agreement between theory and experiment. So next we want to analyze the spectrum of the copper clusters. For that we want to use the copper metal foil as a reference in a way that we determine the amplitude reduction factor for the reference copper metal foil, and then use the same amplitude reduction factor for the analysis of the copper clusters. So for that, we restore the parameters. We go back to refinement, same settings, and now we want to fix the coordination number to 12 and refine the amplitude reduction factor. We just start the refinement, get a good agreement, and obtain an amplitude reduction factor of 0.88 for the copper metal foil spectrum. So this amplitude reduction factor now is what we are going to use to analyze the spectrum of the copper clusters. So file open, and we select the copper clusters, and same procedure, Fourier transformation, and then we can perform the EXAFS refinement. So we select the calculation for copper metal, first shell. We just briefly check the range in the radial distribution function. This is fine. And then we can click on OK. And now as a starting parameter, we are going to use the 0.88 for the amplitude reduction factor. Fix this. Select starting value for the bi-Waller factor and start the refinement. And get a good agreement between experiment and theory as expected. And so those are our values now. Coordination number 10.9. Slightly increased the bi-Waller factor compared to the copper metal foil, and a slightly decreased shift. So if you wanted to compare this now to the same refinement that we did using experimental phases and amplitudes and compare the results, then we can just do this. We open the copper cluster chi of k again, because now we need to select a little bit shorter range, as I explained when we did the refinement first with the experimental phases and amplitudes. Fourier transformation, and now we can do the EXAFS refinement using experimental phases and amplitude, copper K edge, and those are the phases and amplitudes that we obtained during the previous tutorial. We select the range in the radial distribution function and can click on OK and use this as starting parameters now for the refinement. And those are the results. No. Now we can click on history and compare the results that we obtained now from using experimental phases and amplitudes down here and the FEFF calculated theoretical phases and amplitude. And we see we get a 10.8 coordination number using the experimental phases and amplitude and a 10.9 using the theoretical phases and amplitude. Get a very similar distance, and we have a Debye-Waller factor, a disorder, and as I said, this is the difference between the reference and the cluster, so there is an increase of 0.0013 about between the copper metal and the copper clusters, and here we have a Debye-Waller factor of 0.009 compared to the 0.081 that we obtained for the copper metal. So this is also about an increase of 0.013 from the copper metal to the copper clusters. So good agreement here with the results we obtained from using experimental phases and amplitude. So overall, good agreement between the theoretically calculated phases and amplitude and the results we get for analyzing the first shell in the copper metal radial distribution function when we compare those to the results we obtained when using experimental phases and amplitudes. So this is it for analyzing the first shell, and now we want to include the higher shells in the simulation and the EXAFS refinement. So let's close all windows and start again with the copper foil spectrum, Fourier transformation, and EXAFS simulation using the theoretical phases and amplitudes. So now we have all the multiple scattering and single scattering paths here in a list, and most of them are actually multiple scattering paths, recognizable by the n-lag parameter. So an n-lag of 2 corresponds to a single scattering path, 3 and higher, those are the multiple scattering paths. So as a filter, now we can start with decreasing this parameter to show only the single scattering path in this selection box. And then we are going to select the first 5 single scattering paths. This is the range we have here in the radial distribution function. We click on transfer and OK. We need to set some starting values for the Debye-Waller factor. So now I do not want to copy those manually to all the other Debye-Waller factors. This is where this button here, the copy button, is for, which will just take the value wherever your cursor is, take the value and copy it to all the other parameters in this row. So we can do the same with the E0 shift parameter because we have already an idea that 4 should be fine here. So we start with a parameter of 4, copy this to all other single scattering shells and exit. So now this is our simulated radial distribution function, first shell, and also including the higher shells. We can just display the higher shells, and we do see a disagreement currently in the frequency and also in the amplitude, but mostly in this range here. In this range, the simulation does not at all show good agreement with the experimental spectrum. So let's see if we can perform a refinement and maybe adjust this discrepancy here between theory and experiment by fitting the theoretical model to the experimental data. So we go to EXAFS refinement. We just use the single scattering path that we selected. Just have a look at the range. Range is fine. And so now what we want to do is we want to fix the amplitude reduction factor. And now we have a number of distances, Dibber-Waller factors, and coordination number. We want to refine coordination number and distances. We do not want to refine all the individual Dibber-Waller factors. As I said previously, coordination number and Dibber-Waller factors both affect the amplitude of the EXAFS function and are strongly correlated. So what we want to do again is we want to use the Debye model to calculate Debye-Waller factors based on Debye temperature. So again, we use the POT button, which now just puts the Debye temperature here as a free parameter in the refinement, and all the other Debye-Waller factors will now be correlated using this Debye temperature and the correlated Debye model. So yeah, we can start the refinement, and we see the problem remains. We have a poor agreement between experiment and theory, in particular in this part of the radial distribution function. So let's have a look at the simulation and see maybe what multiple scattering paths are present in this range that may have a high amplitude and that may just be required to be included in the refinement in order to match the theoretical amplitude to the experimental radial distribution function. So going back to EXAFS simulation, now we can increase the parameter, n-lag parameter again, and when we look at multiple scattering paths in this range here, we find some multiple scattering paths with very high ratio, so very high amplitude. As I said, ratio of 100, so this is in percent, so this is 46% of the amplitude of the first shell. And so very high amplitude, large contribution to the radial distribution function for this multiple scattering path. So let's transfer it and have a look at what kind of multiple scattering path is present here. And what is immediately noticeable is this angle of 180 degrees. So those kind of scattering paths are called focusing or lens scattering paths because they are basically 3 atoms in a row. So we have a distance of 5.11, but there is another atom just in between the copper absorber and the nearest neighbor at 5.11. And this is the first shell, basically at 2.556 angstrom. The effect of this is that the photoelectron, which is backscattered by the nearest neighbor at 5.11, gets somehow amplified by forward scattering of the neighbor of the copper atom here at 2.56 angstrom. And this results in a strongly increased contribution, strongly increased amplitude of this particular multiple scattering path. So whenever you have and this angle of 180 degrees or 0 degrees, so basically more than 2 atoms, 3 atoms, or 4 even in a row, then this multiple scattering path can in most cases not be neglected. You cannot exclude that from the simulation. You will not get a good agreement between experiment and theory without those focusing multiple scattering paths. So let's briefly reset the simulation and start new. So now we know we need to include the multiple scattering path, at least those focusing scattering path. So we could increase the weight filter now and sort of exclude multiple scattering paths below a certain amplitude contribution from the refinement, and then gradually include more and more scattering paths and see how many of those multiple scattering paths we need to include to get a better or even very good agreement between theory and experiment. For the sake of keeping this video under an hour, I am not going to do this and just select all the multiple scattering paths in this region and see what kind of agreement between experiment and theory we can obtain. So those are the multiple scattering paths I want to include up to 604 transfer. So this is 24 scattering paths now that we include in the refinement. We still have only 5 single scattering paths, 5 shells, and the other 19 are all multiple scattering paths. So this is for the simulation now. We can just click on OK. We can just briefly calculate the Debye-Waller factors from the correlated Debye model, exit, and we already get a better agreement in amplitude here, an overall amplitude between experiment and theory. And this is actually something now that the refinement may be able to handle in terms of adjusting the theoretically calculated radial distribution function to the experimental function of the copper foil. So next now is the EXAFS refinement. We're going to use all those shells, all those scattering paths that we have included. The border now still includes the higher shells. And yeah. So now we have a large number of parameters. We have 29 independent parameters, and we have 74 free running parameters currently in the refinement. So this is not going to give a stable refinement, and now we need to reduce the number of free running parameters by some meaningful correlation schemes. So first of all, for this attempt, we're going to fix the amplitude reduction factor. Also, we want to, similar to what we did before, we want to use the Debye model to calculate the Debye-Waller factor. So we select this. And we still have a large number of parameters now, which are mostly all the multiple scattering paths that we have included in the simulation and now have included in the refinement. The next step now is to not have the multiple scattering path being refined independent from the single scattering path. Well, basically, all the multiple scattering paths have constituent single scattering paths that are included in the refinement, and we can make use of that by basically calculating distances or coordination numbers of multiple scattering paths based on the constituent single scattering path. This is or this can be selected by the MS button here for multiple scattering. So for instance here, for the distances, multiple scattering will color all the multiple scattering distances, indicating that those are now correlated to the constituent single scattering distances. So only the single scattering shells now have free running distance parameters, and all the multiple scattering shells are now correlated to those single scattering distances. We can do the same with the coordination number. This is here, the multiple scattering for the coordination number. So now we have our number of parameters down to 12 compared to the 29 independent parameters. So that is decent. We still have a correlation between the Debye temperature and the coordination number, but that should be fine. With the refinement, we can select the parameter of 4 for the E0 shift as a starting parameter, and then we can give this a go and see that now we actually, let's click on OK, nope. We get a much better agreement between theory and experiment here when we actually include all those single and multiple scattering shells in the simulation and in the refinement. So we get a pretty good agreement here, both in amplitude and particular in the root and the overall shape of the imaginary part. So distances and also amplitude probably agree quite well between experiment and theory. Similar to the analysis of the first shell, the question is now, how can we transfer the results we obtain from analyzing the copper reference foil spectra to the analysis of the copper clusters? And for that, we actually want to fix the coordination numbers in the refinement to the metal foil spectrum and refine the Debye-Waller factors, and then transfer those Debye-Waller factors to the analysis of the copper cluster spectrum. So we're going to restore the starting parameters and start the refinement again. We're still using those 24 shells in this range. And now what we want to do is we want to fix all coordination numbers, because those are then fixed to the crystallographic values. So we just fix them all. We want to refine the amplitude reduction factor. So this is a free running parameter now. And we're going to fix this later in the refinement to the copper cluster spectrum. We want to correlate the multiple scattering shells or paths here for the distances similar to what we did before. So we select multiple scattering here and we refine the single scattering distances. And we want to refine the Debye-Waller factor. So for this refinement, we do not want to use the Debye model and only refine one Debye temperature, but we want to refine the individual Debye-Waller factors for the single scattering shells. We do not want to refine all Debye-Waller factors of the multiple scattering part. Those are too many parameters. As we see here, we still have then 31 free running parameters. That's too many. So we still need to use the same, and this is called averaging here. So basically this averages for the multiple scattering shell, it calculates an average of the Debye-Waller factors of the constituent single scattering shells. And so now we are again down to 12 free running parameters in the refinement. We have the amplitude reduction factor, the distances, and the Debye-Waller factors of the individual single scattering shells. And we can start this refinement. Again, we get a reasonably good agreement between theory and experiment here for the copper metal foil. So the question is now, how do we transfer the results to the analysis of the copper cluster spectrum? If we go back to the parameter box here, we can save all those values basically and then reload them when we analyze the copper cluster spectrum. This is done down here with save. So there's a scheme 1. There are basically 3 slots where you can save parameters from a refinement. We just use the first slot and save those values, basically the values together with the correlation scheme. We do not need this correlation scheme later in the refinement of the copper cluster spectrum, but we want to have the parameters. And so now we can exit this. And next step now is to load the copper cluster spectrum. We do the Fourier transformation, and now we go to EXAFS simulation and basically repeat what we just did for the copper metal foil. So we want to include those 24 scattering paths now in the refinement or in the simulation for now. Can click on OK. So now in order to load those parameters that we just saved, we just have them saved in scheme 1, so we click on load. And this will reload all the parameters that we just determined from the refinement to the copper metal spectrum. Together with those correlations with the schemes all fixed, and so, but this is just now for simulation. We can change those later when we want to actually do the refinement to the spectrum of the copper clusters. So just click on exit, and then we get the simulated radial distribution function based on those parameters that we extracted from the copper metal foil. So next step now is the refinement. Can just select the range here again, and we keep all those scattering shells. Click on OK, and now we can re-enter those correlations. What we want to do now is we want to fix the amplitude reduction factor, because this is the value that we determined for the copper metal foil. And we also want to fix all the Debye-Waller factors, because those are the ones that we determined for the reference copper metal foil. So that leaves coordination number and distances. And as before, we are going to correlate the multiple scattering distances to the single scattering path, both for the distances and also for the coordination numbers. So now the free running parameters are coordination numbers, distances, and the 1E0 shift. That's always free running, which brings it down to 11 free parameters in the refinement. Okay, can click on OK. And this is the kind of agreement we get in this case between experiment and theory when we basically use those Debye-Waller factors that we determined for the copper foil for the analysis of the copper clusters. We can look at the results. Fit results will show all results, the single scattering and the multiple scattering path. If you're not interested in the multiple scattering path, which will probably mostly be the case, then there is a FEFF single scattering option here, which basically only shows the single scattering path and which omits all the multiple scattering path and even assembles the single scattering path in this table, which can be copy and pasted then for record keeping. So this is multiple scattering, single scattering path, EXAFS refinements to higher distances in the radial distribution function. First example for copper metal. This is obviously some sort of a showcase. This is an easier example because there is only one type of backscatterer in a metal structure. And so those refinements, those EXAFS refinement and simulation will become more difficult and more complex when your sample contains more backscatterer, for instance, metal oxides. You have a metal and the oxygen, so heavier and a lighter backscatterer, and also for samples with reduced crystallographic symmetry. So this is high symmetry here, so there's a coordination number of 12, all at the same distance. With reduction in symmetry, we will get more distances. The first shell will, for oxides, for instance, in many cases consist of more than one metal-oxygen distance, and that, of course, makes it more difficult than for the EXAFS simulation and refinement. Those are examples that we are going to look into in future tutorials. But this is it for this tutorial. This is long enough, and nevertheless, I sure hope to see you in the next one.